Okay, good morning everyone, welcome back. So we have 3 more lectures before your presentation. So as you know, at the end of this lecture, we will learn a lot about how to solve optimal power flow. Actually, the topic optimal power flow is the last topic of this lecture. And then after that, you will present your research about papers. So today's topic is about economic dispatch. So let's see. And this is related with what you already learned last semester, but some of you are new here. So even if you know this, I need to go through again. So retail electricity price. There are many fixed and variable costs associated with power systems. So the fixed cost typically involved is related with the investment cost, and the variable cost is related with the fuel cost. So that determines the retail electricity prices. And here when you see is the fuel cost is roughly half of retail cost. And actually, we have different types of price. The price at the wholesale market and the retail price. And the price structure and market structure are different from country to country. And one of the key issues these days is that the generation cost of renewable energy, they have zero fuel cost, right? But they have huge investment cost. That is similar to hydrogen, hydropower. So the cost analysis here, the cost analysis is mostly based on fuel-based generators like thermal power plant. But this kind of analysis may not be applicable for renewable generation. Okay, so in that sense, this is kind of old, but the basic things. So that's why I want to cover anyway. So this is some side information, and it is from California Energy Commission 2007, I guess. And you see the cost of different energy sources, the nuclear, wind, solar, different types of solar, photovoltaic, and concentrating or parabolic through. So this is about solar, thermal heat energy, and ocean wave, and hydro, and geothermal, etc. So when you look at this, this is interesting in the sense that the solar photovoltaic is very expensive. Okay? This is very expensive, but now the cost of PV panel decreases very sharply, and in some country, we say we already reached the greedy parity. Greedy parity means that the cost of renewable generation is equal to the cost of other typical generation. Okay, but no, that depends on country as well. Okay. Anyway, levelized cost of generation, operating cost plus paying of capital, that is like this. So power system economy operation is very important. And it depends on technologies, and different generation technologies vary in the capital cost necessary to build a generator, hydro or thermal power plant, nuclear power plant, and the fuel cost to actually produce electric power. And today you will see some unusual unit for you, which is called the British Thermal Unit, BTU. Okay. There is some historical reason of using that kind of unit, but I will get back to that shortly. So anyway, nuclear and hydro have high capital cost, as you may imagine, and low operating cost. And renewable generation has almost zero operating cost. And by contrast, natural gas means based on the CH4, methane gas. Natural gas generators have low capital cost, but higher operating cost. So and also the core power plant is here. They have high capital cost but low operating cost. So fuel cost to generate a megawatt hour can vary widely from technology to technology. And for some type of the units, such as hydro, the fuel is water, and the cost is almost zero. But that is limited on total available water. And for thermal units, thermal power plant, it is much easier to characterize the cost. And we typically use the quadratic equation to capture the cost of the thermal units. Yeah, so we will focus on minimizing variable operating cost. That means primarily fuel cost to meet the demand. But another angle of the economic analysis is about investment things. Constructing new power plant and constructing a new transmission line. So that kind of planning is important, but requires huge amount of investment. So this is for long-term plan. So from microeconomic analysis perspective, we usually focus on this short-term operation, but this long-term planning is also very important. But I didn't cover that in last semester either. Okay? But that does not imply that that topic is not important. Okay? And then also, if we do well on this operation cost minimization, then we can use that result to long-term power system planning as well. Okay, so power system loads are cyclical. So spring, summer, fall, winter, they have different loads, and also the loads vary even one day. Therefore, the installed generation capacity is usually much greater than the current load. That means the total capacity of generator need to be ready for the worst case. So that means a lot of generation capacity is reserved for unused load. And the level of reserve, the percentage is 20 to 30%. Okay? So I think that is pretty huge. And that means they want to be ready for some contingent events. But maintaining that high portion of reserve capacity increases the cost of the electricity. So if we can operate the power system more efficiently, then we can obviously save money. So that's why we need to do power flow analysis and optimal power flow stuff. So I'm trying to emphasize the importance of OPF in the sense that if you can improve the efficiency, operational efficiency by 1%, then that is really huge if you can really prove it. So the total amount of money spent on power system operation is tens of, one joule, one is $1 billion, okay? $1 billion US. And the sales of KEPCO is around 60 billion. And I guess half of that comes from purchase of the energy, okay? And then, okay, let's say 30 billion. And if you improve by 1%, you can save $0.3 billion, and it corresponds to how much? 3,000 won. Okay, so this is really huge number. So improve by 1%. You may think this is, hey, what's that? In my paper, I can improve 30%, 40%, sometimes. So, but in reality, in power system, if you can improve, and this is for sure, then we can save huge amount of money. Okay? So, yeah, and because there are different types of energy sources, we can meet the demand in various ways. So we want to find the way that minimizes the total generation cost. Okay? And that is, again, related with optimal power flow stuff. Since different states have different mixes of generation, we will consider how generally to minimize the variable operating costs given an arbitrarily specified portfolio of generators. So again, just simplified version of that, and the cost of the generator is modeled as a quadratic function. But before going to that, let's look at summer versus hydro generation. The two main types of generating units are these two. But wind and solar rapidly increase these days. And for hydro, the fuel is free, the water is free, but there are many other consideration on operation, like a fixed amount of water available, and reservoir levels must be managed and coordinated, and the downstream flow rates for fish and navigation, that's also important. So hydro optimization is typically long-term, like many months or years. So, this is a long-term thing. We want to focus on a short-term operation. Okay. So we have several generator types, like again, nuclear, hydro, thermal unit, and natural gas, and renewable generation. And they have different capital cost and different operational cost. And the important part is that the electric load changes over one day. Okay, so this is when you sleep, this is when you walk. And we are around here, I guess. So I have a chance to go to some museum in Scotland, and I found that they emphasize energy so much, the clean energy, renewable energy, and one of the reasons is because James Watt is Scottish, and he invented a steam engine. Actually, he improved the efficiency of steam engine, and that was the beginning of industrial revolution. And anyway, so in the museum, they have some game that match the supply and demand for kids. So that game has 4 different types of energy sources. So I can show you that. And nuclear, and hydro, and core power plant, and renewable generation. So you see. Can you see that? So there are 4 buttons. Nuclear, core, wind, and solar. And interestingly, the load changes over time. So kids are requested to adjust the generation to satisfy the demand. So sometimes they are asked to reduce the generation, sometimes they are asked to increase the generation, and sometimes the kids are trying to generate more solar, but then the warning comes out, hey, this is during night, there is no solar at all, something like that. And when the kids succeed satisfying supply and demand for more than 60% of time, then the job is complete. So very interesting. Kids can know the importance of matching supply and demand. Okay, so I took a picture that a mom and a kid is playing the game. You see that? So obviously, this little kid does not know what she is doing, but maybe later she realized, hey, there was that. Anyway, so because the load changes over day, and we have we need to mix different type of generation. The first one is the nuclear power. That is the cheapest one, but it is not easy to control the output power of nuclear generation. So that serves the base load. Okay, so the output of nuclear generation is constant. So that serves the base load. And for the mid load, then you can use core power plant. It can easily change the output of the generation. And the core power plant is more expensive than nuclear power plant. But for this part, this is the peak load. And during the duration of this peak load is not that much. So during this time period, all the core power plant are used here. So the additional power comes from natural gas-based power plant. And that is the most expensive one. So that's why the electricity price changes over time. Because for each level of load, we will see that the marginal cost of generation changes. So to satisfy this load, the level of generation, the amount of generation changes, and that also affects the price. Okay. Oh, combustion turbine used only for several hours. What is the meaning of combustion? How is it different from steam engine?
엔진은 그냥 물을 끓여갖고 끓인 물 증기갖고 터빈을 돌려갖고 그렇게 전기를 만드는데 컴버션 터빈은 그냥 불을 갖고 연소가스 나오는 거예요.
Yeah, so today morning I asked GPT-4 what is the difference between steam engine and combustion engine? Yeah, steam engine, we boil water and the steam rotates the turbine, right? And then using the Faraday induction law, electricity is generated. Combustion is actually controlled explosion. So inside a cylinder, fuel meets air, oxygen, and then explosion. So the difference between combustion and steam engine is that in combustion engine, this explosion happens inside in the cylinder, but in steam engine, that's not. So that's why in your car that is called internal combustion engine, which means the explosion happens inside the engine, inside the cylinder. Okay, but in the case of steam engine, steam power plant, that's not the case. Anyway, so natural gas, that's expensive one. Okay, so this is block diagram of a thermal unit. We have a boiler. So using some fuel, you can boil water and you get steam and you can control this valve. So by controlling this valve, you can increase or decrease the speed of this turbine rotation. And then based on Faraday law, electricity is generated. And interestingly, Faraday, where is he from? I really don't know where is he from. Faraday. Is he from British or America?
London.
Yeah, so I think that's very interesting point in the sense that 영국 대륙, England continent. So you may heard this before. So they are the British people. I think they emphasize experience a lot and experiment. So Faraday is one of the example, and James Watt is another example. James Watt, invented the steam engine. By contrast, France or Germany, what does this imply? You know many famous mathematicians, Poisson, Laplace, and philosophers, Descartes, Pascal, etc. Okay, so they are focused on reasoning or theory, and they focus on practice. Okay, so and this is an example of practice invented by James Watt. Actually, James Watt did not invent a steam machine. He improved the efficiency of the steam machine by 3 times. And original steam machine was for water mill, so to pump the water. But James Watt changed the structure so that it can be used for other applications, and that ignites the Industrial Revolution. Anyway, we have another interesting part here, auxiliary power. So the generated power, the P gross minus auxiliary power is actually the net generation that can be supplied to power system. What is it? This auxiliary power is again used by this turbine. Okay? This engine also need to consume some electricity as well. Okay? So that's why when we have blackout, we have another black start generators that can supply some electricity initially. Okay? And when this engine goes on, it can generate the power that it consumes. That is called auxiliary power. Okay, so to optimize generation cost, we need to develop cost relationships between net power output and operating cost. This operating cost comes from fuel cost. And between 2 to 10% of power, 2 to 10% of power is used within generating plants. And this is known as the auxiliary power. So we have several curves to observe today. So input and output curve, fuel cost curve, heat rate curve, and incremental cost curve. Actually, they are simple, but with different names. So let's see one by one. By the way, I told you BTU, British Thermal Unit, and this corresponds to 1058 joule. And obviously, 1 megabtu is 10 to the 6 BTU, and 1 BTU is then 0.29 megawatt hour. So other than this one, is it correct? Is it correct? Okay, thank you. Other than this, so we are used to joule using the unit of MKS, but practically, calorie is used a lot. Similarly, BTU is used a lot, and the reason is because, what is BTU? British invented steam machine. Okay, so at the time, they were interested in how much energy do we need to increase 1 pound of water by 1 Fahrenheit degree. That is 1 BTU. Okay, because they did not use kilogram, they used pound. And they did not use Celsius degree, they used Fahrenheit degree. Okay, so 1 pound for 1 Fahrenheit degree increase, how much energy do we need? That is 1 BTU. Okay, and that is converted like that, and that is converted like this. Okay. So this is I/O curve. I/O means input and output curve. And this is input. This is output. Okay. So, but no. Why this is output? The output of generation. So generate the power. Okay. This is output. And this is input. Input means the fuel of the generator. Okay. So actually what it says is to generate this much of power, how much fuel do we need? So this is called I/O curve. Okay? So, and the I/O curve plots fuel inputs in mega BTU per hour versus net megawatt output. So can you see what kind of line it is? It is a straight line or not? 민재. It does not look like a straight line. Okay. Yeah, actually this is quadratic. Okay, so you see this, the slope is slightly increasing, but it looks almost like a linear. But here, even if the generation power is zero, still the thermal power plant need to consume some fuel. Okay, so there is a fixed cost. So this is the amount of fuel, and that can be multiplied by the cost of that fuel. For example, for core, 1 mega BTU is $1.7. Oh, pretty cheap. I see. Later, you will see that 1 pound of core corresponds to something. Okay, so core looks like this. 1 pound of core. Yeah, so corresponds to how much energy we will see. Okay. Anyway, 1 mega BTU is just $1.7, pretty cheap. Okay. Then heat rate curve is just the average fuel cost. So this is the fuel cost to generate some amount of power. For example, at this point, you can just think of this slope. Okay, and the total cost of the fuel divided by the total generation. Okay, and that is called the heat rate curve. So this is just this is not the derivative of this curve, but just the average slope at each point. Okay, so very, very high slope, and the slope is decreasing, and then at some point it touch, and actually almost same. So you see the slope is steep, but no decrease minimum, and actually almost same. Okay, so the unit of y-axis is mega. So here, the unit is dollar per hour, and this is mega BTU per megawatt hour. And anyway, yeah, the same thing. And finally, incremental cost or marginal cost curve is like this. So previously we have this cost quadratic function, and if you take the derivative, you have this marginal cost curve. And this marginal cost curve is linear, and yeah, it slightly increases as the output power increases. Okay, so here the unit is, okay, this is a megawatt, and this megawatt hour per dollar. So you may think, hey, this is watt. So the unit is power. This is per megawatt hour dollar. Why is that? Because here what it means is that if we produce power for 1 hour, then we need to consume some amount of fuel, and so that this means that. So I told you James Watt is Scottish. James Watt. I emailed you. You didn't read it. You didn't read it. So to memorize James Watt, we use this unit, watt, as a power unit. Okay. So mathematical formulation of cost, The generation costs are usually not smooth. However, the cost can usually be adequately approximated using piecewise smooth functions. So typically we use this quadratic function. I didn't see this cubic function, but maybe some other some types of generator has cubic functions. Or we can use these piecewise linear functions. But we prefer to use this quadratic function because this is easier to analyze. So if we assume this quadratic function, then the cost is given like this: fixed cost, a linear cost, and quadratic term. But the thing is, this gamma is very small. Okay, so as you see here, this is a marginal cost. So this slope is gamma, and this is beta. Yeah. And this fixed cost does not affect short-term operation, but actually it affects what? So for short-term operation, we assume that the generators are on, so we only focus on the output power, but this term is important when you consider whether turn on or off the generator, right? Because when the generator is on, it constantly consumes this amount of power. When the generator is off, it does not consume any money, right? So the turn on and turn off decision is also important, but this turn on and turn off has some constraint. The ramp up rate, the constraint. It takes time. And also turn on and turn off, turning on and turning off also costs some money. Okay, so we need to carefully decide whether to turn on or turn off in terms of money and time. So, and yeah, the marginal cost is just the derivative of this. So, yeah, this is a core usage example. And let's see, 500 megawatt. That's a typical number for thermal power plant. And the efficiency is 35%. That's also typical efficiency of thermal power plant. So 30 to 40% is the traditional, the typical efficiency. And some very high efficient generator can achieve 60% of efficiency. As you visited Dangani power plant, that has that is combined two types of different generators. You remember that, okay? So that achieves very high efficiency, but typically 35%. Then, what about internal combustion engine efficiency compared to the big thermal unit? How much? 10 to 20%. Right. So the efficiency of big thermal unit is 2 to 3 times higher than internal combustion engine. Okay? According to GPT-4. If that is not correct, please blame GPT-4. Then what about the efficiency of electric vehicle compared to internal combustion engine car? So the efficiency of electric vehicle is 60%. Okay? And internal combustion engine car is 10 to 20%. So at least 3 times more efficient. Anyway, so 35% efficiency. It is being supplied with core costing $1.7 per mega BTU, and with heat contents 9,000 BTU per pound. So 1 pound of core corresponds to 9,000 BTU energy. Okay? Interesting an example. So what is the core usage in LBS is the unit of pound. Okay, you know that? Right? So what is the core usage in LBS per hour? And what is the cost? So here, assuming 35% of efficiency, okay, 500 megawatt hour energy, and the efficiency is 0.35. So divide by this. So we need to generate this amount of energy, and actually that is this one. And then we want to convert. Actually, this is not same to this one. We need to use the arrow. So this amount of megawatt hour need to be converted to mega BTU. So divide by 0.29, and we have this amount of mega BTU. And then 1 pound corresponds to 0.009 mega BTU from here. So divide this by this one, gives us that amount of core per hour, and the cost is multiply this by the unit price and that much. So when you look at this number, megawatt hour just $16, or it means kilowatt hour, how much roughly? If $1 is 1,000 won, then kilowatt hour corresponds to 16 won. Very cheap. Core is really cheap. Okay, so these days the S&P in Korea. Okay, normally it was 100 won per kilowatt hour, but these days it has increased up to 160 because of the fuel price increased. But compared to this one, just 16, core is 16. Okay, so you see the core power plant is very cheap, but we cannot use core power plant more because it generates carbon dioxide, right? So because of the environmental issue, we need to discourage the generation of using coal power plant. Okay. Incremental cost example. By the way, I think we have an interesting example here. Where is it? Maybe, yeah, this one. Yeah, wasting core example. Assume, hey, a 100 watt lamp. That's too big. In Korea you use 60 watt lamp, but just 100 watt lamp is left on by mistake, as you usually do. Okay, it turned on, it kept on for 8 hours, even if no one is inside house. And that electricity is supplied by the previous core power plant. And the transmission distribution losses are 20%. Yeah, that's huge, typically not that much. So how much core can she waste it by letting the 100 watt lamp on? Actually, yeah, you have a 260 watt lamp on, then almost like that. So with 20% losses, 100 watt load for 8 hours requires 1 kilowatt of energy. Okay, good. Yeah, this times that is the total amount of energy divided by 0.8 gives this amount of energy, and because the efficiency is 35%, so divide by that, and I want to change this to BTU, so kilowatt change to megawatt, and that is changed to BTU, and BTU in pound, and it gives you this number. So 1 pound of core corresponds to roughly 1 kilowatt hour of energy, roughly speaking. So, by the way, then, how much is it, 1 kilowatt hour? Your air conditioner, the consumed power of air conditioner is typically 1,000 watt or 1 kilowatt. Okay? or the heater consumes 1000 watts typically. So if you run that for 1 hour, that corresponds to 1 pound of core. But this is very cheap, as you see. Yeah, that's the problem. Anyway, I'm interesting, motivating example why we need to save energy. So, incremental cost example. These are a typical number for 2 generators, 1, 2, okay? So the 1020.01 blah blah blah. I guess this is a core power plant and this is what? It increases more rapidly than this, so this may be from natural gas. Anyway, you can have this kind of 2 different types of marginal cost. So if the output of this one is 250, this is 150, then the total cost is like that, and the marginal cost is like that. This is obvious. Okay, any questions so far? No. Then let's talk about economic dispatch. Actually, this economic dispatch is very easy for you guys, I hope, assuming you are familiar with optimization. Okay, so this is just a typical convex optimization because the cost function is convex function and we have just a single equality constraint such that the total generation, the sum of total generation equals to the demand. Okay, so this economic dispatch, okay, by the way, what is the meaning of dispatch? What is the meaning of dispatch? Yeah, right, yeah. So economic dispatch means 경제 급전. Dispatch means generation of power, okay? So we want to find the most efficient way to satisfy the demand, okay? So the sum of the generation equal to the total demand plus the line losses in the transmission network. So this is our constraint, but we want to minimize the sum of all the generators, okay? And anyway, this is quadratic function. We have a single constraint, so this is an easy convex optimization problem. So, and yeah, actually on constraint minimization, even if we have this constraint, it starts from on-constraint minimization. And so when we have objective function, you take the gradient. And if there is no constraint, then the optimal point can be obtained where the gradient is 0, right? And the gradient comes, is like this. So, by the way, so when we have constraints, then we need to use the Lagrange multiplier. So this is a typical form of optimization, objective function and constraints. So we need to satisfy these constraints, so we construct Lagrangian. Lagrangian is such that the difficulty of solving optimization is coming from these constraints. So rather than having these constraints, we multiply this by some variable, which is called Lagrange multiplier, lambda. So we construct another objective function like this. So this another objective function is called Lagrangian. And then given some lambda, some parameter, this is on-constraint minimization, as you see. So given some lambda, you can minimize this easily, especially when this function is convex. So take the gradient of Lagrangian and find a point where this gradient is 0. So given lambda, you can minimize this Lagrangian. And the question is then, what kind of lambda can we use? Okay? And the lambda we need to pick up is the optimal lambda, the optimal Lagrange multiplier. So at that optimal point, we have, in this example, we have 2 conditions. The first one is the Lagrangian at the point, the gradient of the Lagrangian should be 0. And also the gradient of Lagrangian with respect to lambda is also 0. Okay, so gradient with respect to x is 0, and gradient of Lagrangian with respect to lambda is also 0. Okay, so these two conditions, okay, this one and that one. So actually, this is equation and this is another equation. So when you solve those two equations, you can find the optimal x and optimal lambda. So x is called primal variable and lambda is called dual variable. So in this simple example, this is the example. We have a cost function, and this is constraint, and that is multiplied by lambda. So we have Lagrangian. So take the gradient with respect to primal variable. Then you see that, by the way, we have m number of generators. So take the partial derivative with respect to PGI. So you have this one. And because we have PGI here, lambda is here. Okay. So interestingly, you see that for m number of generators, we have this equation, but still the same lambda here. So this means that at the optimal point, the marginal cost, the derivative of the cost function, should be all equal, and that is same to lambda. Okay? So that's why this dual variable Lagrange multiplier can be interpreted as a price, right? And then how can we determine lambda? Well, interestingly, when you look at this, as long as you know this cost function, actually, you know the cost function, this PGI is expressed as a function of lambda, right? So, and we have this constraint. And then this PGI is a function of lambda. So then by changing lambda, you can satisfy this equation. Actually, by changing lambda, you can change the output of generators. So by changing lambda, you can increase the price or decrease the price. Then the output power of each generator changes, and at some point, you can satisfy this one. So as long as you know this cost function, you can easily find the optimal lambda. Yeah. So this is the example. Yeah, the cost function 1 and 2. And two conditions, the modular cost should be equal to lambda. So you have this one and you'd have that one. Yeah, this is pretty easy because this modular cost is just linear. So PG1 can be expressed as a function of lambda. Similarly, PG2 is expressed as a function of lambda. And the sum of PG1 and PG2 need to satisfy 500 megawatts, so lambda can be determined easily. And then, yeah, you can do that. So this is the solution. Optimal output of generator and the Lagrange multiplier. And so this gives you how to solve numerically, but the same thing can be interpreted using called lambda iteration solution method. Well, the lambda iteration solution method means that how can we find lambda that satisfy this one? But actually that's pretty easy. So in this figure, by the way, you have a function. You have a function of lambda. Okay, so this is just a function of lambda. We have a single variable, and we need to satisfy this. How can you find it? PG is some function of lambda. This is just another types of root finding algorithm, just like this one. Fx equals 0. This types of problem it is. So we have PGI, this is a function of lambda, and summation I, this should be equal to PD. Right? So same thing. So simply, you can apply bisection approach first. which does not require the derivative of this function, which is very robust. But if you can apply the derivative, you can find the solution more easily. So this is about bisection search. So anyway, we have a function, we have an intersection, this is a solution, and let's say this is the optimal lambda star. Then we start from some range that gives you the minimum value and the maximum value. And we are sure that we can satisfy the demand when the price is within this range. Okay? So just applying bisection search. Well, intuitively speaking, if the price is too small, the generator tries to generate less or more? Less, right? And the price is high, the generator tries to generate more, right? So by changing this lambda, we can change the output of the generators and can, at some point, satisfy the demand. Okay? So this is based on bisection search, which is robust because it does not require the derivative. Okay. So this is the illustration of lambda iteration graphical view. So the minimum price and the maximum price, and then we change the price. And when the price is given, this is the marginal cost of each generator. So for given price, the output power of generator is determined like that and like that. And then sum of that can be greater than the demand or less than the demand, and then change the lambda value. Lambda iteration. Example, you know what it is. Okay? Yeah, you know all this, so I don't want to repeat. Yeah. So that's a lambda iteration, and let me stop here. And